This talk is on managing stream sensor data for mobile equipment prognostics. It's a collaboration between mechanical engineering, computer science, and statistics, with data provided by an industry partner from the mining sector here in Western Australia. Your co-presenters are Deborah Correa and I am Melinda Hodkowitz. Studies suggest we will have 125 million connected cars on our roads by 2020. Consider the diagnostic and prognostic potential from the data these cars are streaming. Here in Western Australia, we already have access to streamed sensor data on industrial assets such as mining trucks and excavators. However, many equipment manufacturers' predictive maintenance solutions are immature. And our asset operators have found it difficult to access and process the raw data from these machines, and hence are not getting the data-driven insights they need for maintenance actions. This project has datasets from 13 excavators measured over 9 months. This totals 300 million rows of data in 19.9 gigabytes of files. Each excavator has 58 numeric sensors and 40 binary indicators. In addition to this stream sensor data, we also have two other important data sources. First, the Fleet Management Database is a database into which the operator enters machine status codes such as waiting, loading, scheduled maintenance, and also various events of interest such as hydraulic faults. And we have the computerized maintenance management system, which has work orders describing maintenance events that are actually performed on the excavators. We're going to spend a bit of time describing the data. The structure of the sensor data in its original form is known as long-form data. This is shown in a table on the left. As you can see, there is a column displaying timestamps and a key column to identify the sensor each row refers to, and then a third column specifying the value for that sensor at a specified time. The desired or complementary structure is shown on the bottom right, and this is known as wide-form data, where each variable or sensor is separated into unique columns with a timestamp identifying each row. Wide-form data is required to aggregate or manipulate the variables. The process of converting long-form to wide-form data is known as pivoting. Streaming data, like the long-form data we show, has a number of unappreciated challenges. The sensor recording intervals differ between sensors, with some polling values as often as every 5 seconds and others every 30 seconds. Furthermore, the polling times are not synchronized between sensors. Rearranging the data into a wide format creates many empty values because each row corresponds to a particular time that only a select few sensors have recorded values for. To this data, we still need to join the fleet management data. This is ordered by time, with each row containing a start and end times, and these must be matched between the fleet management records and with the sensor data. As you expect, the timestamps do not match exactly. And data must also be drawn from the maintenance work orders in the computerized maintenance management center and matched at the right time. When we do this, the file size resulting from conventional pivoting and alignment of time becomes 17 gigabytes for a single excavator for 9 months. In addition to the size issues, the pre-processing like this also results in many rows with at least one NA value. These NA values cause complications later in the modeling stage. This is just a quick example to show what currently engineers working for the partners look at. In this example, this is just sensor data for a hydraulic oil tank temperature over 4 days. Imagine trying to look at all of this data for 58 numeric sensors and 40 binary indicators across 272 days for 13 excavators. It's impossible for engineers to monitor this volume of data visually. We need computer science and data analytics to help us. So let's look at the data. This figure shows 9 months of data for the hydraulic system on one of the excavators. On the left, shown in blue, is data for the oil temperature sensor, and there are 4 alarms. pump transmission oil level alarm, pump contamination, an oil overheat, and an oil level alarm. On the right is the status of the operator entered hydraulic fault condition. What I want you to notice is how very difficult it is to visually see any patterns in the first 5 columns with the response variable or hydraulic fault condition on the right-hand side. If I were to look at this, it's not easy for me to see when I would think a hydraulic fault was about to occur from looking at the rest of the data on this page. So the question we are faced with is, how can streamed sensor data be efficiently transformed and compressed and then used to inform maintenance on mobile equipment, given the sort of data set that we have just described to you?
So let's have a look at our data cleaning pipeline. All this is done in Python. In reshaping the data, we extract timestamps and values to separate files and pivot each file separately. We do the same for the SMMS and the fleet management data. This results in 145 files per excavator, each with a time column and a value column. The combined size of these files is only 30 megabytes as opposed to 17 gigabytes, resulting from conventional pivoting and alignment of time. Then we apply a technique from financial modeling called OHLC to compress the data. This is described in the following slide. The OHLC data from all 146 files is then combined into wide form to a common timestamp and then made available for the models. We then explored data-driven and engineering-based variable selection and a variety of models. The most prospective thus far is the use of a log linear mean regression model for time-to-event prediction. The sensor data is summarized by adapting the method behind financial open, high, low, and close OHLC charts. These charts are used to show price variations of stocks in a specific time window. The open and close values together show the direction of the price movement within this window, and the high and low values give an indication of volatility. The sensor data is manipulated by taking the first and the last values of each sensor, as well as the maximum and minimum for each 1 hour period, similar to the manner in which price data is manipulated to create OHLC charts. This allows the key trends of the data to be represented with less entries, as we can see in this plot in the slide. A period of 1 hour is chosen as it is expected that a failure will show symptoms multiple hours before it occurs. Now, we are going to talk about something of general importance to all in the prognostic health management community. It has proved hard to make effective predictive models using this dataset. And this doesn't make sense given the volume and the variety of data that we had from the machine. However, think for a minute about what we are trying to predict. We are trying to predict a failure event that has not yet happened. In our case, a hydraulic fault. First, we use a code in the fleet management called hydraulic fault. But this is not operator-generated code. It is the perception of an individual operator that a hydraulic fault is likely to happen. Is this a good response variable? What else could we use? We also consider the maintenance records. In this case, the date the unit was removed from service to work on the hydraulics. Again, there are a number of people involved in this decision. So, we have 2 potential response variables. Both involve human judgment. There is no ground truth as the failure has not happened yet. The companies doing analytics on mobile equipment streaming data are using the code entered into the fleet management system, in our case the hydraulic system fault code, as their response variable. But this code is human generated by an operator. and we have many operators operating the equipment. Do they have the same mental model for how the equipment works? Obviously not. What we can show here is that almost no agreement between the fault logged into the fleet management system and any maintenance work done on that system, even allowing a time lag for the work order to be processing. We'll see now in this slide that this challenge with having a human-generated response variable is apparent in the poor predictive performance of the models. First, we explored models commonly used by data analytics groups in the companies we work with, noting that we have used models that account for the time dependence of the covariates. This slide shows, for instance, the logistic regression model, one of the many standard machine learning models we developed for this dataset. The y-axis shows the probability of an event, and each event is shown as a yellow dot. You can see that we get near perfect fit in the training data, shown in black. In other words, we are overfitting. However, the ability of this model, shown in blue, to predict is not good. 3 were events not predicted using CMS as the response variable, and several events predicted but not occurring in the fleet management data. We had similar poor performance behavior for other models. We suggest that the inconsistency and maybe invalid entries by the operators for the response variables are a major factor here. There is no ground truth as the failure hasn't happened yet. Now we are exploring some more sophisticated statistical models. In this plot, we have on the y-axis the reliability function of the excavator and the calendar time on the x-axis. The model estimate is based on the excavator condition at time t, and this explains why the reliability function is not a monotonic function. The red lines indicate the events. For the training data shown as black dots, we can see that the reliability function is approaching to 0 in almost all cases when we are close to the event. The blue dots are the test data. This is equivalent to what the operator would see in the real-time system. There are 2 events in the test data. Note, we had a long period without any sensor alarm data. We can see the reliability function is approaching 0, close to the failure for the first event in the test set. For the second event, the model did not give a clear indication of the failure. Under all the constraints that we have discussed, we consider that this model has potential to be a useful tool for real-time monitoring once we resolve the response variable issues.
So, what did we learn from the modelling? We noted that traditional models for event prediction that we made were overfitted and had poor predictive power. For our log linear regression model, the most influential covariates for predicting hydraulic faults based on the response variables from, firstly, the fleet management, and secondly, the CMMS data, are not what we expected. We didn't get hydraulic oil temperature tank, pilot pump pressure, hydraulic oil level low alarm or overheat indicator or pump contamination indicators did not feature prominently as influential covariates. This is less surprising than you might first think. Recall earlier, we look visually for patterns in the data relating to the hydraulic fault alarm, and there were none. Think about where this data comes from. The hydraulic fault alarm that we are trying to match as a response variable is generated by a human, the operator, and his or her perception about an event that has not happened yet. Remember, it's a hydraulic fault, not a failure. So what do we conclude from this work? First of all, the data was really messy, and most of our time was devoted to transforming and compressing the data set. Secondly, if you don't have an actual failure, what are you using as your response variable? Ask yourself, is a human involved in determining what this response variable is? In our case, both the fleet management and the CMMS data are based on operators' Firstly, perceptions. What do they consider potential failures? And actions. When did they choose to report them into both of those systems? We know human data are not consistent for prediction purposes. We suspect also that data analysts may not realize that the fleet management entry is actually human generated. As a result, lots of time has been wasted in trying to build predictive models on asset data sets with poorly defined, often operator-defined response variables. From all of this, we suggest that asset owners should consider having data engineers who understand how to transform and compress the data and can ask questions about response variables to ensure consistent pre-processing of asset data and the selection of good response variables for subsequent modelling. In conclusion, both Deborah and I would like to thank you for your attention. We would like to acknowledge our co-authors on this paper, Toby and Adriano, our industry partner, and the Centre for Transforming Maintenance Through Data Science. And I would like to make a personal thank you to the BHP Fellowship for Engineering for Remote Operations for sponsoring my work. Thank you.